Welcome to lecture 4 of environmental chemistry. Today we're going to talk about the first part of thermodynamics, talking a little bit about the fundamentals, and then in the next lecture we're going to talk about some specific examples on in the context of more practical kind of thermodynamics. So far we had one key term for each lecture. So the first lecture was all about entities or species. The second lecture was about the activity of species. The third lecture was about how these activities or entities are related to each other. We define the equilibrium constant. And in this lecture, the key terminology is basically the system and energy. And then we're talking about the system itself, and then how the system is exchanging energy with the surrounding. And I brought this mug to drink coffee, also to demonstrate some of the concepts that we talk about today. So this will be our system. So it's a boundary inside this universe. So anything outside of this would be surrounding. This is whatever is inside is the system. So we're going to focus on that. Specifically, we're going to talk about fundamental understanding of several key energy-related parameters. Also, we're going to talk about the first and the second laws of thermodynamics, and then talk about the equilibrium constant we had in the previous lecture, but from the angle of energy. So quickly overview what we talked about. We had this general terminology for describing a reaction, which has some stoichiometric coefficient, some reactant, and then some products. And then we describe how these entities or species are related to each other using equilibrium constant, which basically relates the activity of the products to the activity of the reactants. And it was at equilibrium, it was K. If it wasn't at equilibrium, this would be a reaction quotient or the Q term. So if you remember in the previous lecture, we looked at K from the kinetic angle. We talked about the fact that this means the ratio of rate of going forward and backward with the reaction. So more within the context of kinetics. But here we want to approach this from the energy point of view. When we talk about energy, it means we're talking about thermodynamics. So the focus of this lecture specifically will be more on the fundamentals, driving some equations that probably some of them you've seen it before, but it's good to approach it from the beginning and then see how we can use that for an environmental system. So before we start, just a quick question. Any energy-related parameter that comes to your mind when we talk about energy? Anything related to energy? Enthalpy, so that's one of the main parameters that we're going to talk about today. Anything else? I would add internal energy. What was that? Chemical potential energy. So chemical energy. This is also something that we're going to talk about today. Also entropy, something that is related to energy. And these are just some examples of those terminologies related to specifically the energy. So some formal definition of thermodynamic or fundamentals of thermodynamics is basically a quantitative study of how energy is transformed from one form to another. So this is basically the whole field of thermodynamics. And what we're interested in is basically the relationship between chemical potential energy and heat. So this is something that we're going to talk about today. And also, we aim to determine the extent in which reactions will occur under certain conditions. So that's another factor that we're going to talk about at the end of the lecture. So to start with, there's also, I think, the zero law of thermodynamics. I'm not sure about that, but we normally start, when we talk about thermodynamics, it starts with the first law. which you've seen it before, is basically the conservation of energy. We know about that from general chemistry, that energy can neither be created nor destroyed. So it's basically going from one form to another. So this is the basics of the first law of thermodynamics. And when we talk about, in this lecture, talk about the anything related to thermodynamic of a system, we're specifically talking about this key terminology, which is basically the system, as I mentioned. So it's basically system is a piece of the universe. Very simple. It has boundaries. Anything outside of that would be basically the surrounding. So we're going to use this two terminologies very often. So this has to be closed, but for some reason it's not working well. Let me see. Okay, so it's basically an enclosure. So anything around that would be the surrounding. So very intuitive, very simple. Anything in this universe, not in this classroom, anything in this universe beside this volume would be the surrounding for this particular system. So then we can define the total energy of the system. So this system, for example, this mug has, first it has two phases, some gas phase on the top, some liquid in the bottom. In the liquid phase, we have sugar, we have coffee, and we have water. And for the gas phase is nitrogen, oxygen, and some other gases. So, but we can define a total energy associated to the system. And when we talk about the total energy, or the term E, we're basically talking about all the microscopic energy plus macroscopic. So then zooming in the microscopic energy, then we have to zoom in to the system. So every system, it has some entities inside. Let's say these are the simple mechanism or the simple molecules that are inside the system. So to define the microscopic energy, so these are energy associated with the molecules at microscale. So the first one that you've seen probably is basically the molecules can move. So this is basically the transformational energy. What else? Something related to the micro scale feature of the molecules. Obviously, they can move around. What else? Can they rotate? Molecules can rotate, so basically some of them are related. So related to the rotational. So this would be rotational energy. What else? Exactly, vibrational, so they can vibrate. That would be vibrational. One more. So the binding forces. So if we combine all of them together, we call this internal energy. So basically the internal energy associated with the system. So this would be or U, the term U. It makes sense. It's all about what is inside the system. So, and all at the microscopic level. But then here, the total energy can also have some macroscopic energy. So it really matters if I'm putting this mug here or on the floor. So sort of a gravitational energy, or it matters if I'm moving it around or if it's just sitting there. Kinetic kind of energy. I'm adding more components of macroscopic components of energy to the system. So it impacts the overall energy of the system. So the macroscopic could be basically other sources. For example, this is basically could be kinetic, it could be potential. Electric field sometime. So the absolute value of energy is one thing. The change in energy is another thing. So that's basically, right now this has some energy. I'm moving it. So there is another state of energy. So these are two absolute values, but then the change is something that we care the most in this lecture. So the change of one state to another state of energy. And because of that, for the environmental system itself, it's fair to ignore the macroscopic energy. For example, when you talk about the lake, the potential energy doesn't change much. It's always at the same elevation, or nobody's moving around the lake, or it's not exposed to an electric field, for example. So for environmental systems, so basically macroscopic energy is neglected. Again, because we are mostly interested to know more about the change, and then that factor is not changing. So the total energy is equal to the internal energy. So it's very hard to calculate the internal energy because we need a lot of information about the molecules. We need to know about the transformational energy. We need to know about the composition, so calculating the binding forces, the vibrational, and also rotational. So it's very hard to calculate that. But then, as I mentioned, we're interested to know about how the internal energy is changing from one state to another. And if we can connect that to something that is very easy to understand, very easy to measure, and very easy to implement, then it would be very useful. And when we talk about that, we have to connect the change in the internal energy to something that, again, is measurable, is easy to manipulate, and it makes sense. And that's basically this very important relationship, which talks about the change in the internal energy of a system and connecting that to heat and work. Again, something familiar. Heat we can easily measure. Work we can also define and measure. So something very useful. I can change. It's hard for me to measure the quantity of internal energy of this mug. But then I know if I apply some heat, what would be the delta U without knowing the beginning and the end, because I have this very important relationship. So for Q term is basically the term, the heat term. the heat exchange between the system and the surrounding. And the work is basically the kind of, or often consider the P delta V kind of work. So those work that is resulted in a change of the volume of the system. And specifically, if we again talk about our system, the system could exchange heat, either release heat or we apply heat to the system, and it can perform work, or work can be done on the system. In terms of the signs, for Q, that heat entering the system, the sign would be positive. And obviously, if the heat is leaving the system, the sign would be negative. And for work, this is basically work by the system. Then it would be positive. Positive, work by the system. Eventually to reduce it, yes, exactly, because this is a negative sign here. Okay. So again, this system, we apply heat, internal energy goes up, obviously, and if we just leave it there, it's releasing heat to the environment, the internal energy goes down. And the same thing for work. So here in this case, the volume is not changing. So this is sort of a isovolumetric kind of interaction. Or sometimes I have a very good isolation around that, so it's isothermal. So there's no heat exchange. So depending on that, we can define basically a different system in terms of whether they're exchanging heat, work, both, neither. So it could be one of those cases. But this equation applies basically to all of them. So far we knew about the change in the internal energy and how that's related to some factors that are very familiar to us. So now is a good time to define the very first important thermodynamic factor, which is enthalpy, or H. It is basically a property of a thermodynamic system. It's sum of the system's internal energy and also the product of pressure and volume. So it might be a little bit confusing, but if we formulate that, H basically, the enthalpy term, is the internal energy plus PV term. So this is basically the internal energy. This is the pressure. And this is the volume. So this pressure volume term is basically, it's the work required to establish the system's physical boundaries. So the bigger the volume of the system, it requires more work to build it, and also the same thing for pressure. But it's heavily connected to that internal energy that we just talked about. So similar to the internal energy, we really don't work with enthalpy itself much, rather change in enthalpy. That's something that we want to eventually connect that factor also to something that is measurable or something easy to apply, specifically Q or work or W. So we have the relationship to drive the delta H. We basically need to do delta on both sides, U plus PV. Then it would be just a mathematical expansion, delta U plus delta PV, or delta U plus P delta V plus V delta P. Anything here that we had before with that? Yes, but let's leave this alone, like this aside. This guy, we already have an expression, exactly. So then delta H would be Q minus W plus P delta V plus V delta P. So this is the general expression of the enthalpy term. Probably you've seen enthalpy to be just simply a heat expression. So it's associated with the heat to the system or releasing from the system. As you see, that's more specific, but this one is basically the general expression of the enthalpy. So in many systems, including the aquatic system, most of the time the processes are isovolumetric, or they occur at constant pressure. Yeah, they occur at constant pressure. So what it means is that for aquatic systems, but again, let's consider that lake. Whatever happens in terms of the reaction, the expansion of the volume of the lake as a system is not significant. So it's fair to assume delta V of the system is equal to 0. So that's one factor. So there's no work associated with that as well. That kind of P delta V kind of work. Also, the reaction inside that lake, it doesn't result in changing the pressure of the lake as a system. So delta P is also almost 0. So because of that, delta H is equal to only Q. So this is the expression that you're familiar with. So that delta H is that Q term. Is because of that, because the system we're dealing with, it's isovolumetric, and also it's basically the pressure doesn't change much. So again, we achieve our goal of connecting something that was a little bit vague, delta H, to something that is easy to understand, to implement, and to measure, which is basically the heat to the system. So based on that and what we've learned from general chemistry, we can now talk about or classified chemical processes based on delta H. So we have exothermic processes. They basically exhaust heat. So as I mentioned, heat from the system to the surrounding has a negative sign. So then delta H would be negative. So this means it makes the surrounding warmer. The classic example is basically combustion. Again, it's all about the system and the surrounding. For an endothermic process, basically is opposite, delta H is greater than 0, which makes the surrounding cooler. Any example? Melting of ice, so it's absorbing heat. Yeah. or evaporation. So only relying on delta H, we can tell whether a reaction, for example, is exothermic or endothermic. So only delta H. We're not talking about entropy or Gibbs free energy that we're going to talk about later. So relying on only on delta H, we can talk about the nature of the reaction. And a quick reminder, enthalpy is also a state function. So that means it's basically, it's not a path function. Measuring enthalpy is not easy. Rather, change in an enthalpy can be measured easily because it's all related to that Q term. If you want to calculate the enthalpy, then you have to follow this. Then you saw that the U term is difficult to measure because it's all related to that microscopic features or energy related parameters of the system. Okay, so that's all about the first law. It's all about the conservation of energy, basically one form of energy to another form. So the first law established the principles of energy conservation. However, our ultimate goal is to predict whether certain changes in chemical system are thermodynamically favorable. So to make it a little bit easier, so it's basically the second law. What it says is whether a process is spontaneous or not. So that's the key consideration or simplification when we talk about the second law. So the first law, we focus mostly on enthalpy, but now we have to bring entropy to the equation because that's something that dictates basically whether the process is spontaneous or not. You might say it was the Gibbs free energy from the general chemistry, not the entropy itself. But later you see that when I talk about entropy, it depends on what kind of entropy we're talking about, the system, surrounding, or the universe. So the exact definition of entropy, it's or the technical definition might be a little bit confusing, but I try to simplify it here. I know you have a very good understanding of entropy to just connect it to disorder. So that's basically a general expression of entropy. But to be more technical, it's basically a measure of system thermal energy per unit temperature. So you'll see that later in the next page. But this is the description, and it's basically for unavailable for doing useful work. So to just a quick reminder, when we talk about entropy, we always consider that disorder that we talked about. For example, if we consider these three phases of solid, liquid, and gas, so we can basically move between the three systems by, for example, applying heat. So if we have these three phases, then we have more orders in solid, we have a little bit less in liquid, and then we have more disorder in gas. So basically going from solid to liquid, we're increasing the entropy. Going backward, obviously, decreasing the entropy. The same thing here. Or as we go from solid to gas, what happens is basically we're increasing entropy. Or disorder. So what the second law says is basically for anything to happen to be spontaneous, it must result in increasing the entropy of the universe. So the entropy of the universe is always increasing. So basically, if we consider this volume as a system, then anything in this universe as the surrounding, then we can define the universe to be the surrounding plus the system, right? So then the change in the entropy of the universe, or delta S of total, is equal to the change in the entropy of the system plus the change in the entropy of the surrounding. Just making it short. So basically we have, again, the system, surrounding, and then overall it would be just the universe. And now based on the second law, for a spontaneous system, then delta S of total must be greater than 0. So that's basically what we had from general chemistry. Was again a kind of delta G factor must be a negative value to have like spontaneous system, but here is delta S. And the key here is basically the total. The entropy, the total entropy of the universe for a spontaneous system, for a spontaneous process, is always increasing. It's neither the system nor the surrounding. So I guess it was either a homework question, or an exam question, that for a spontaneous system, can we have like a negative delta S of the system? So it seems we could, but it always, the entropy of the universe has to increase. Can we travel in time? That's probably this year's exam. So then we have to talk about forward or backward. Forward, I don't know, maybe, yes. Backward, hell no. Why is that? We can't go back to yesterday. The entropy of the universe yesterday was less than today. So if we go backward, it's against the second law of thermodynamics. So that's basically from the Big Bang theory. So that entropy was, there was a lot of order, and now we're going towards more disorder. So delta S is always increasing. So one of the reasons that we can't go backward in time is against the second law of thermodynamics, because the total is decreasing if we go backward. And that's not a spontaneous system, okay? So now it seems this is very good. If we calculate these factors, then we can look at the sign and see if it's negative value, then that, it's a positive value, that process is spontaneous. If it's negative, it's not spontaneous. But what's the problem with this one? Like, to deal with these guys? I have a good understanding of the system. I know what is in my system. I know there's coffee, there's sugar, there's water, and some gases. And I might be able to describe the change in entropy of all the elements of the system. But can I do the same for the surrounding? Can I calculate the same thing, the change in entropy, for anything in this universe beside the system? So that's the difficult part. difficult part is this one is related to the surrounding, and I don't have any information, or I have very limited information about the surrounding. I have a good information about the system. So if we can connect the surrounding change in entropy to a system level parameter, then I can basically calculate these two to be able to calculate how this process is impacting the entropy of the universe. So that would be the next part. So Mr. Gibbs, I don't know his first name, he did it and basically saved us some time. Sort of the goal was to connect delta S of the surrounding of this room, how it's changing if I'm exposing it to some system, which is this one. And the key factor here was basically this line. For any change in the system at a constant temperature and pressure, the entropy gained by the surrounding, so delta S of the surrounding, equals to the enthalpy loss of the system, so I'm connecting it to the system, divided by the temperature. Again, using that definition of the entropy. So what we just mentioned, is basically delta S of the surrounding is the change in the enthalpy of the system divided by the temperature. So this is the key bridge between delta S of the surrounding and delta S of the system that we are looking for. And this is basically derived from first the definition of entropy, and second is basically derived from the first law. So I don't know what happens to the surrounding, but I know delta H, or the heat exchange between the system, if it's at a constant temperature, divided by the temperature of this system, eventually gives me how much I'm impacting the surrounding, just by simply using the first law. Whatever is happening here would be equal to the total disruption of the surrounding without specifically looking at the surrounding. So now that we have this one, so we can just basically replace what we had in the previous page. Delta S of total would be equal to delta S of system minus delta H of system divided by T, or minus T delta S of total would be delta H of system minus T delta S of system. So the good part about this specific relationship, is basically it's all about the system. So I really don't want to measure or consider the surrounding. I'm just using the first law to drive everything based on the features of the system. So now we can use this description to talk about whether a process is spontaneous or not, because we know the sign of this guy. Then we can calculate these values for the system and then basically look at whether that value is negative or positive. One thing that Mr. Gibbs did was basically defining this Gibbs free energy, or delta G for the system, to be equal to, so this is a definition, delta H of system minus T delta S of system. So that's basically that G term is the Gibbs free energy. Delta G is obviously the change in Gibbs energy, free energy of a system, or how much energy is available to do work for a system. And that's basically connected to entropy and enthalpy. So comparing these two, it's obvious that delta G of the system now is related to features of the total of the universe. So for a spontaneous process, we mentioned that delta S of total must be a positive value. And we know temperature is always greater than 0. It's a Kelvin, temperature in Kelvin, an absolute temperature, which is always a positive value. So then this means for a system to be spontaneous, delta G of a system must be negative. I'm sure most of you've seen these variables before, delta G, and the fact that delta G has to be negative for a process to be spontaneous. But this doesn't mean anything. What it meant was basically delta S, or entropy of the universe, must increase for a spontaneous system. Make sense? So up to here, we distinguish between the system and the surrounding. We connected the two together. And from now on, we're only talking about the system. So we want to dig deeper on what is inside the system, the components. So far it was a system level. After the components, at the end of the lecture, the reactions between the components. So that's basically the following steps. Because always talking about the system, I'm not going to use this subscript anymore. But just keep in mind, it's always about the system from now on. Okay, so let's start with defining something that is very important, and that's basically the chemical potential of species I. So again, system, now we're zooming in on the individual components, sugar, coffee, water, and the gas phase, individual phase in the gas phase. So the chemical potential of species I, so basically a chemical potential of species I, is the energy that can be absorbed or released due to a change in a particle number of a given species. So this might be a bit confusing. Let's make it very simple. If I add 1 unit of sugar to this coffee, it increased the sweetness factor, right? It would be more sweet compared to the current state. So how much it changes that factor is basically that chemical equivalent to that chemical potential. So to talk about more specifically about species I, if I add 1 mole of species I, or if I remove 1 mole from the system, then how much that G factor is changing? The overall Gibbs free energy of the system is changing. So the dependency of the system to that specific entity. So we can then define this chemical, or that G now for species I. We're using that bar to talk about the normalized factor. Then it would be the total G of adding that 1 mole of N. So we introduce 2 elements to that G factor. One is we are specifically talking about a unit or 1 species, and then it's normalized. So that bar, whenever you see it, it's normalized. So that means this one that doesn't have I and this bar means it's for the total, and also not for the specific entity, but rather for the whole system. As we know, the system has sugar, also coffee, and other I factors. So the overall the GI, all the energy associated to sugar is basically the normalized of sugar, so per mole of sugar, times how much moles of sugar I have in the system. So this would be the total Gibbs free energy associated with having sugar in the system. Not 1 mole, but the total amount of sugar. Again, pay special attention to this bar, this I, and later this standard condition. Later, but not for now. So this is total I, total sugar. We can do the same thing for other components. So basically, if we expand this, then the total G of the system would be all the GIs, which means all the normalized GIs times Ni. So this is basically the total system. So now we can expand whatever we had and use whatever we had in the previous page for a specific entity inside the system. So for each entity in the system, we have that relationship of delta Gi per mole to be delta H minus T delta S. So this is one of the main relationship that we're having in this lecture. So I'm going to highlight those that you need to put all together and then see what is the difference between different expressions of this delta G factor. So this one is for species I and for the normalized factor. And now you know how to play with normalized to not normalized for species I, and then going for the total of the system. So similar to the activity that we defined as baseline, to define that as a sort of a baseline, and then we compare everything to this baseline is a common practice. There's also a common practice here to define a zero level for G and H, or what is the zero level of G for a specific element, and then we can compare other elements at other conditions to that specific zero level. So for example, here for oxygen, it has to be the oxygen gas at a pure oxygen at 25 and 1 atmosphere. At that level, we call this one the standard condition. So this is basically that the new symbol you see per mole for species I, which is O2 in this case, then it would be equal to 0. So that's basically the ground level. And later, if we have the information for that ground level or the zero level, we can basically talk about any condition based on the concentration or based on the deviation from the standard condition. So this might be a little bit confusing now, but just bear with me. It's you'll see that later. It would be pretty straightforward. So for oxygen, the zero level oxygen at 25 at 1 atmosphere in a pure gas form. For H and G. But then for S, it would be not a zero value, but we can basically define, we have that value in table. So that's basically the good news here. And this F here is the formation. For now, we don't really need to talk about that. Just keep in mind, this is standard per mole for I. There's a table that provides all the values, and for the exam, obviously, I'm going to provide that. So we really don't cover the third law of thermodynamics in this lecture, but basically what the third law says is at entropy of 0 at the absolute temperature of 0. So the perfect crystalline structure would be basically what we have at the temperature of 0. So this is another example of G for different elements at the standard condition per mole. But as you know, G, we need an expression to talk about G values for a specific entity at non-standard. And one common practice is basically to have a relationship that has the standard component plus some condition component. So if we have that kind of expression, the standard condition is coming from the table, and the condition parameters is basically what we're at. So, and the expression is basically this one. For GI per mole at any condition would be equal to GI at the standard condition per mole plus RT ln of the activity deviation of I compared to the activity at the standard condition. The activity of the standard condition, this would be 1. Therefore, what we have is basically GI at any condition per mole would be GI at the standard condition plus this deviation. So that's the second important relationship here. So you see that this is a very key relationship that, for example, you want to calculate G per mole of, let's say, ammonia gas at a non-standard condition, some concentration or some activity. Then what you need is basically this value from the table, this guy. Then you know how much you have in terms of the activity, you know what temperature you're talking about, and this is basically a constant. Then you can calculate specifically for that condition for the element I, or for the species I. So this is very, very important, and it gives us that ability. And many of the equations that you see, for example, the Nernst equation for electrochemical system is basically similar philosophy. You have at non-standard condition is related to the standard condition plus some deviation from that standard condition, temperature and activity here. So far we defined delta G. We talked about specific G per mole for species I at standard, non-standard. So all the individual components of the system, we can define G. But now let's talk about reactions. So if, let's say, coffee is reacting with sugar, we know how to deal with coffee and sugar individually based on what we have so far. But now we want to just play also with the reaction, because reaction tells us how these elements or entities are connected to each other. So now we want to use that to be able to derive delta G for a reaction. So delta G of a reaction is also an extremely important information for a given system, and specifically for a given reaction in a system. So to do that is basically we can drive this about, I'm going to just give you the final expression. Delta G of a reaction. Now we have this R term, not necessarily I term, per mole. Then it would be basically a combination of all the G I per mole, considering their stoichiometric coefficient. So that stoichiometric coefficient is basically similar to that Ni that we had before. It was correcting for that impact. So this would be basically the stoichiometric coefficient, and this would be basically molar. It's a molar, so Gibbs energy of species I. So this is at any condition. We have also the same expression for delta H and delta S. So this would be then very useful. Delta H of R per mole would be basically the same thing considering all the H. And delta S of the reaction would be also very similar. So we can have this expression of delta G of reaction is equal to delta H of reaction. Again, in terms of the expression, it's not something new. Basically, we're talking about the reaction here in this case. So these are, again, the important relationships here. If it's a little bit confusing in terms of the terminology, I mean, in the next lecture, we're going to solve for an actual reaction. And if you know the logic, it would be pretty straightforward. This means, this guy, and whether this is at standard or non-standard, it would be just pretty logical. So this was for any general condition. You know, if we're specifically looking at the standard condition, this would be basically the same. So delta G of the reaction at the standard condition would be also VI for all the GIs at the standard condition. And similarly, we have delta G of reaction at the standard condition would be delta H of reaction at the standard condition minus T delta S. This would be. So the workflow is like, let's say the sugar is reacting with coffee somehow magically. The first thing is we calculate GI per mole for sugar. Then to do that, we need to use that GI standard condition plus RT-ln of the concentration of sugar. That means the concentration is important, the temperature of this media is important. So once we calculate this, we know the stoichiometric coefficient of the reaction between the two. I do the same thing for coffee, and then combining the two would give me delta G of the reaction between the two at non-standard conditions. I can do the same thing basically here for H and delta S also. So quickly we can apply what we've learned here into a hypothetical reaction. So this is basically a hypothetical reaction of AA plus BB goes to CC. We can talk about delta G of reaction per mole. This would be all the stoichiometric coefficient of all the entities at non-standard condition. So now we can expand this. Keep in mind the stoichiometric coefficient for the products are always negative, for the reactants are always negative, for the products is always positive. So we're consuming A and B. So we're consuming, so this would be minus A of GA minus B of GB. We would produce C of GC. Sure. The stoichiometric coefficient is basically for all the reactants is a negative value. So this would be minus A minus B. It's just a mass balance. So you're consuming that. So in terms of the overall mass balance, it would be minus of that factor times the concentration or whatever factor we're talking about. And then you're producing this guy. So what we did was basically expanding this one to all the I or species in the reaction. The next step is basically we need to know about these guys based on the concentration and also the standard condition, just expanding 3 times for these entities. So basically what we have is minus A, then GA at the standard condition per mole plus RT ln of the activity of A. The same thing for B would be G0 of B plus RT ln of B plus C GC standard plus RT ln of C. I'm using again one of those expressions we had, how to calculate G for species I per mole at non-standard condition based on the standard value we have. So I can rearrange this a little bit. Basically minus A GA standard minus B GB standard plus C GC standard plus RT minus A ln A minus B ln B. Okay, this has to be capital A. And plus C ln C. What is this expression? Exactly. So this is basically all of this would be delta G of the reaction per mole at the standard condition. The same expression as we had on the top. So we can a little bit play with this one. So mathematical operation, we arrange it in this way. So now what is this guy? So are we at equilibrium? Not necessarily. So this is Q. Exactly. So this section would be Q, or the reaction quotient. So it seems what we have eventually is delta G of R for a reaction is delta G of the reaction at the standard condition plus RT ln Q. So this is another important relationship. So again, you're seeing a similar expression. Some factors at any condition is related to the standard condition from plus a deviation from the standard condition. So it seems it's also true for the reaction. Again, for the reaction, it would be easy to calculate this guy because we have these factors from the stoichiometric coefficient, and these are from the tables. So you can quickly calculate this. You know how to calculate Q, and you have the temperature. So it would be very straightforward to talk about a very important factor related to your reaction, which is basically how much energy you're exchanging overall per mole for this reaction. So a very, very unique information. So in the previous lecture, we talked about the equilibrium constant, that K value from the kinetic point of view. The rate of going forward is equal to rate of going backward. So what we talked about was eventually K equal to K forward divided by K backward. So this is the description of equilibrium from the kinetic point of view. But now, if you remember in the previous lecture, we talked about the minimize or energy level when we reach the equilibrium. Or specifically when we talk about equilibrium, using the expression that we developed so far, at equilibrium, delta G of the reaction is equal to 0. So this basically the reaction is at equilibrium if delta G of the reaction, not delta G of the reaction at standard conditions. So because that value is all depending on the table values, not here. And if we insert this into what we had here, so basically at equilibrium, delta G R is equal to minus RT ln of K, because Q is equal to K. So then, and this was equilibrium constant. So you just define again equilibrium constant based on the Gibbs free energy at the standard condition. Again, this is a very important information because this value is basically very easy to calculate. You have this expression, for example, here. These are the standard values from the table. So you can quickly calculate this guy, and then you also calculate the K value. So K, it opens door to relate different species together, as you know. So one type of question would be you have analytical tools to measure the concentration of species at equilibrium. So you basically let it run. We assume it's dilute. You calculate or you measure the individual concentration. When you do that, you can basically have this expression and calculate the K value, right? Then based on that, you can calculate delta G of the reaction at the standard conditions. Or it could be opposite. You have this information here. Then for example, you don't know the distribution or how the equilibrium is established. Based on this relationship, you can predict that also. And this is also the key relationship in the other course that I teach on electrochemical engineering. Is basically this value is related to the standard potential also. But again, the same logic. And from the standard potential, we go to the actual potential, and this is called Nernst equation, similar to this one, a deviation from the non-standard condition. So this is a very good practice in terms of establishing those thermodynamic relationships. Again, just a quick note, at equilibrium, delta G R is 0, not delta G R of at the standard conditions. So those relationships that I highlighted in this course, in this lecture, we're going to use them in an actual reaction in the next lecture, and then try to combine delta G's of different reactions, like what we did for K values in the previous lecture. So the flow of this presentation was, first we started defining a system. Then specifically for the system, what we did was defining the total energy, which included macroscopic, microscopic. Then we narrow it down to just the internal energy, just considering that internal energy is a better way to approach in terms of the environmental systems. Then we mentioned that the internal energy is hard to measure, or it's not really that useful, but rather the change in internal energy is something that we can deal with. And then the way we were basically manipulating this one, it was basically through applying heat or performing work. So this was, then after delta U, we also connect this one to delta H, or like H value. We define entropy. Then we brought this PV term to the table. Then we define delta H, just the change in entropy. And then here we basically talked about the heat exchange versus the change in enthalpy. And up to here was mostly talking about the first law. Then we brought entropy to the table, delta S, and then we defined basically delta G based on that, which was basically the second law. And in terms of G, we first defined G for individual species at the standard condition per mole. Then we use that expression of that value plus RT ln of the concentration. We define GI at any condition per mole. Then we use that to describe delta G of the reaction at non-standard condition, and we know how to do that. And then eventually we connect this one to Q, which was K at equilibrium. So fundamentals of thermodynamics cannot be summarized in 1 or 2 lectures. It's by itself. I took 4 thermodynamic courses in my undergrad and grad time, so it's a very comprehensive field. But today we just try to talk about the very basic fundamentals, the first law, the second law, and later we're going to use this for the environmental chemistry and all the other fun reactions that we're going to cover in the following chapters. Any question? Okay. If not, these are the further readings, and then next time we're going to talk about the practical thermodynamics.